Waalaikumsalam, Doctor.
So today we continue with our psychometric punya material. So we go to the last part of the psychometric, which is the air conditioning processes. So let me share my screen with you all. All right. So in air conditioning processes, we can see that there are several processes can be defined in the air conditioning system. And these processes are usually represented by the direction of the process, which we can sketch in the psychometric chart. Okay. So if you look right here, if we have point A and we go to the left of the psychometric chart, whereby from the dry bulb, okay, from the dry bulb temperature, we go to the left, whereby the temperature will decrease. This is called as the cooling process. Horizontally to the left is cooling process, whereby from the initial point where we go to the right horizontally, that is called as the heating process. Okay, so heating and cooling process is only involving what is being called as the sensible heat, whereby we are only changing the temperature. But as far as the moisture content is concerned, the specific humidity, it's still the same. The moisture content is still the same, whether we are going to the left or going to the right. To the left is a heating process. Sorry, to the left is cooling process, and to the right is a heating process. Okay, and then we have another horizontal up and down type of process, whereby this up and down we have the change of the omega value, whereby if we have humidifying process going up from the initial state here going up, meaning that we are going to change the omega value. So this omega value usually being changed by producing a spray inside the air flow. Okay, while this against of this humidifying process is the dehumidifying process, whereby we are going downward. Usually when we going downward, meaning that we are going to condense some of the moisture inside the air. So we have condensate. Meaning what? Meaning we are going to reject the condensate from this dehumidifying process, where we are going to look what is the change in the omega value, the decrease in omega value. And apart from that, we have still two more processes, which are the diagonal type of processing going up, the combination of heating and humidifying. Okay, so this type of process in the air conditioning system is to increase the omega value, whereby we are going to heat it up. At the same time, we are going to spray some water inside the airflow. While the opposite of the heating and humidifying process is the cooling and dehumidifying, whereby it's going downward. We have dehumidifying together with the cooling process. So these are the 6 types of processes that we could have in an air conditioning system. And this can be elaborated a bit more on this diagram. So this is humidifying going upward from X to A, and then from X to B is dehumidifying. From X to C is cooling process, and then from X to D is the heating process. So this is a very basic process, whereby if you look at this cooling and heating, omega is constant, while the humidifying and then the dehumidifying, the dry bulb temperature is constant. Okay, and then we have a dehumidifying from X to E. We can see that the delta, okay, the delta omega, the omega value will change, and at the same time also the temperature will increase from B to E. So this is the increment of the temperature. While the cooling and dehumidification process is X to F, we still have the decrease in delta omega, the omega value will decrease and the temperature of the air also decrease. So meaning that if we want to have heating process, we need a device to heat it up. Okay, we must have a device to heat the air up. So usually we are going to use a electrical resistant. While the cooling process, we are going to have a cooling coil. Okay, we are going to have the cooling coil. So we are going to look at these processes very in detail. Okay, so this is the value of temperature, the dry bulb temperature. This is the value of a change in or the value of omega, omega F and omega B. On the top part is omega C and omega E. And then we have the TE and TB, the temperature of dry bulb. And then also we have the temperature of dry bulb for the cooling process, TC and TF. So when we project all the line horizontally, this is what we have. When we adjust or we project the line vertically, this is what we have. Of course, the other is the enthalpy, the dew point temperature, and etc. So for the case C, X, and D, we are going to have the omega value is constant. Okay. So from the energy conservation, from the mass conservation, we are going to look at the mass balance equation, whereby if we look right here, for the mass of air in is equal to for the mass air out. It is for a single stream and steady flow device. So this is what we have being called as the conservation of mass. And then after that, we are going to look at the energy balance, okay, whereby we can have right here the energy balance in terms of mass transfer. We have the Q in, we have the W in, we have the summation of the enthalpy or the energy going into the system, and we have equal to the Q out, W out, and the summation of the energy transferred by mass at the exit or the outlet of the duct. So this is two basic formula that we are going to use to look in terms of the mass flow rate involved and also the energy involved in those air conditioning system. So this is our first air conditioning system that we have, which we are going to have heating process. Okay, in Malaysia, we seldom use this type of process. It's still air conditioning, but it doesn't involving the refrigeration system. It's only involving the heating process. So in a heating process in air conditioning in temperate country, so this is our duct and this is our heating coil. Okay, so this is the condition at point 1 coming into the duct before touching the heating coil. This is our value of the outlet. So inlet, we have T1, omega 1, P1, the dry bulb temperature, the specific humidity, and then we have the relative humidity. So we have the Q in, right? The Q in from the heating coil. So in this case, we are assuming that this duct or this pipe or any internal flow, we assume that it is being insulated, or the process from 1 to 2, we assume is adiabatic. There's no Q loss. If we have the Q loss, then we have to take care of the Q loss involved. But in this case, the Q from the heating coil is going to heat up the air from point 1 to from state 1 to state 2. Okay? So if you look at this process 1 to 2, let's say begin at 30 degree and then it's going to be, this is not heating, this is cooling. Okay, this is cooling process. You see the decrease in the temperature. So this is point 1, this is point 2. If we analyze the relative humidity psi 1 and psi 2, we are going to have the psi 2 is greater than the psi 1. Right? And then of course, for a cooling process, the final temperature will be lower compared to the initial temperature. And for this case, it's horizontal line, meaning that the omega is constant. There's no condensation occurs in this case. So if we have the direction of this process is to the right, then we have the heating process. Okay, we have the heating process, right? So in this case, if we look at mass conservation, the mass in is equal to the mass out. Okay, m dot a1 equal to m dot a2, m dot a2 is equal to m dot a, meaning that we have only one value of m dot. And then as far as the relative humidity is concerned, is constant. Then if we look at this energy balance equation, so what we have is the SFEE. Okay, this is basically the SFEE. What is energy in? What is the energy out? And then what is the energy transfer in or transfer out? In this case, we are going to have only the energy transfer in by heat. So in this case, we can write the energy balance equation is m dot h1, okay, plus q dot 12, and then is equal to the final energy, which is the m dot h2. And when we rearrange this equation and to be q as our title, then this is q12 is equal to m dot multiplied by h2 minus h1. So how to get the h2, h1? We could get the h2 from this psychometric chart, project the point 1 to point 2, project the point 2 for the enthalpy, then we could have the difference in enthalpy. All right? So that is how we use for the heating process. This is the diagram for what we call as the heating with humidification. Right? Sometimes when you see, I don't know, my experience, I have one time that I went to one restaurant whereby it's very hot, okay? And then what they do, they have a sprinkler, very fine sprinkler, which is from a very fine nozzle. What the purpose is just to add up the moisture content in the dry air so that we are going to have drop in the temperature, right? So this is the heating coil, assuming that this is our environment condition. From point 1 to point 2, we are going to heat it up. And then after heating process, we are going to find that the P value of the RH is going lower. Then we are going to increase the P value, the RH, by introducing the spray of water vapor. Okay, spray of water vapor. In this case, it's called as the humidifier. So this humidifier could be a sprinkler, or this humidifier could be a steam. Okay, steam from a boiled water. Okay, we introduce the steam. So as far as the mass conservation is concerned, the m dot 1 equal to m dot 2 is equal to m dot 3, which is the m dot for air. We assume that the air portion of m dot is greater than the mass portion of the water vapor. So we assume is equal to m dot A. And then if you look at the point 1 to point 2, there's no introduction of moisture. Then we have the omega 1 is equal to omega 2. And we know that there's no moisture involving, so point state 1 to state 2, this is only involving sensible heat. That is the increment of the temperature. So this can be represented on the psychometric chart as point 1 to point 2 horizontal. So the sensible heat is being used in order to increase the temperature from 10 degrees C to 22 degrees C. And if we project to the right, then we are going to have the omega 1 is equal to omega 2, right? Because of this heating process, we are going to bring down the value of Phi, or the relative humidity. Then after that, from step 2, we are going to mix the air with moisture. Okay, from this humidifier, moisture. Then what happened? we are going to increase the amount of air contained, the vapor contained in the airflow. Therefore, we are going to increase the omega value up to state 3. Okay, up to state 3, whereby in this case we are going to heat it up, or sorry, we are going to heat or to increase the temperature as we are going to have the RH as 60%. Okay, so this is the process from point state 2 to state 3. Of course, when we have all the state being defined on the psychometric chart, then we could get what is the Q. So in this case, we are involving two types of Q. Okay, Q12 and Q23. What is Q12? In this case, the Q12 is m dot A multiplied by H2 minus H1. And then another H that we are going to have is the Q23. What is Q23? Is equal to m dot A H3 minus H2. So we have two phases of heating or Q involved. And what is the delta omega? The increment of the humidity, the relative humidity is omega 3 minus omega 2. So this is the amount of air, of water that we are going to sprinkle. Okay, this is the amount of water we have to sprinkle, which is the m dot A multiplied omega 3 minus omega 2. Okay, so this is basically based on what? Based on the mass balance. Okay, mass balance. Right, so this is a mass balance omega m dot W, which is being produced. This is the content of moisture at state 2. This is the moisture at state 3. Okay, inlet, add out, outlet. Okay, so this is the energy balance. This is the mass balance. So this is called as heating and humidification. Right. Now we look at an example from the book. In this case, we have the initial state is at T1 10 degree, Phi1 30%, and the mass, the volumetric flow rate is 45 meter cube per minute. And then we have the state 2 where we heat it up to 22 degree. So the T2 is at 22 degree. And then after that, we are going to sprinkle to add up moisture content. So it's going to bring up the temperature as T3 25, and we are going to bring up again the humidity, relative humidity as 60%. So this is the sketching on the psychometric sketch or diagram. But this one is what I'm going to look is on the same question, but we are going to plot on the psychometric chart. Okay, so when you plot on psychometric chart, then you will have all this value. Okay, all this value. And the question asked for part 1 is the rate of heat supply at the heating section, which is the H2 minus H1. So we need the enthalpy 2 and 1. Okay, so this is basically based on the analysis, based on the analysis, not psychometric chart, based on the analysis. So in this case, we are going to have the P set at 10 degrees C, and we have going to have the P set at 25 degrees C, and this is the HG at 10 degrees C, and this is the HG at 22 degrees C. Okay, so to calculate what is the Q12, so this is the formula. Q12 of the Q in at the heating section is m dot A H2 minus H1. So this is how we get the m dot. All right, we got the m dot A. So basically, we are using the formula of m dot A is equal to the V dot 1 divided by V1, where the V1 is the specific humidity. The specific volume. So we need to get the m dot a from state 1 because that's the given parameter of this volumetric flow rate is based on the state 1. And then how to get the V1? The V1 we are going to get from the IGES, ideal gas equation of states, where we know that the V1 is equal to RA T1 over PA. So we need the PA value. Then to get the PA value is basically to look at the phi, or the relative humidity. Right? From this relative humidity, we are going to have the P vapor 1, the partial pressure of vapor at point 1. And then after that, we know the P value. Then we can get what is PA1. So this PA1, we are going to get it, put it inside this V1 equation, then solve for the V1, then solve for the M dot A. And then after that, we are going to look also into the omega 1 because we need the omega 1 to be put into the enthalpy equation. What is the enthalpy equation? For state 1, for the air plus moisture, this is CPT1 plus omega 1. That's why we need the omega 1 right here. And multiplied by HG1. So what is a CP? CP is CP for air, which is 1.005. And then the T1 is 10 degrees C. Okay, 10 degrees C. And please remember, this equation, we need to get this equation. The temperature we are going to use is in degree Celsius. Don't convert to the Kelvin. Use directly 10 degrees C. Right? And then what is omega 1? Omega 1, we have 0.0023 and then multiply by Hg1. What is Hg1? Hg1 is equivalent to the Hg at Hg1. This is, we got the temperature of V1 is 368. Okay? 3.368. Water vapor P set at 10 degrees C. With PV1 0.368. Okay, so meaning that right now we are going to have the value of Hg1 is basically at 0.368. What is the value? 25. Sorry, yeah, at 10 degrees C. Okay, at 10 degrees C. So this is the value, 2.5 Hg at this 22 degrees C for H1. This is for H2. 241, I think it's sub right here. Yeah, okay. This is Hg at 22 degrees C. And then 25. Wait. H1 is equal to Cp, okay, omega 1, Hg1. In this case, Hg1 is equal to 2519. 2519 at 10 degrees C, yeah. Is equivalent, is according to the state 1, While the state 2, this is Hg2. The Hg2 is basically at the 22 degrees C. This is 24, yeah, that's right, 2441. Okay, Hg at temperature given. So this is the H1 value, this is the H2 value. Okay, and then we could get what is the delta H, and after getting the delta H, then we could get what is the Q in. So that is the point for the first one, right? And then B, the mass flow rate of the steam required in the humidifying section. So meaning that we are going to involve the omega value, right? The omega value. So this is the omega, the mass balance for water. Okay, this is water at state 2. This is the add up of the water. This is the water at state 3, water content. So we want to get what is the MW. So this is the formula for MW. Then we need to define what is our omega 3. So this is the formula to get the omega 3. Okay. And then once we get the omega 3, we can solve what is the M dot W. So meaning that we have to put in 0.539 kilogram of water or water vapor for every minute. Okay, for every minute. Right. Now, that is based on what? Based on the mathematical analysis. So next, what we are going to look, we are going to try to sketch the processes on the actual psychometric chart. Okay, psychometric chart. So now we are going to sketch the first state. The first state is 10 degrees C, 30% RH. So we plot the 10 degree. So that is the 10 degree. And then we have the RH. Okay, so that represent the RH is about 30%. So you can see here, this is RH for, I think it's 20, right? It's not mistaken. And this is 40. So in the mid, so this is 40. So this is 40 represent, no, this is 30. Okay, 30. You can, guys, can you plot this in your psychometric chart later on? Okay, I'm just showing you. Then that should be 0.1. And then we try to get 0.2 at 22 degrees C. So this is 0.1. And then we are going to sketch the 0.2. The 0.2 should be horizontally equivalent to omega 1 is equal to omega 2. So this is the process from 1 to 2. Okay, to the right, 1 to 2. So that is the process. And then after that, we are going to have the temperature at 25 degrees C. So this is the temperature at 25 degrees C. And then we are going to plot, or we are going to get it at 60%. So 60% RH, that is 60% RH. Then that should be our state 3. So this state 1, state 2, state 3. So we could have, this is the process. 1, 2, the pass of the process, 1, 2, 2, 2, 3. Okay? So that is the process. That is the numbering, the states. Then when we want to get what is the value of omega 1 and omega 2, that is the value. And then we want to get what is the omega 3, that is the value of omega 3. Okay? And then that is the enthalpy for H1. And then next we have the enthalpy of H2, because we need the enthalpy in order to get the Q12. Q12 is equal to M dot A multiplied by H2 minus H1. So that's it. Right? That is a process on the psychometric chart. And in this case, we need to get, if you want to solve using psychometric chart, you need also to do some mathematical analysis. Okay, you do have to do some mathematical analysis. You cannot get everything basically 100% from the psychometric chart. There must be some mathematical analysis involved. Okay, any question, guys? Okay, this is the example of our real condition. Okay, our real condition in Malaysia, where we have the air conditioning, we have the evaporator, which represent the cooling coil, the evaporator, and we do have condensation occurs at the evaporator side. Okay, so let's say the air coming into the duct, the aircon duct is at state 1, and state 1 is at 30 degrees C, relative humidity 80%, and the volumetric flow rate is 10 meter cube per minute. Right? Then if we look here carefully, when the air enters the duct and in contact with the cooling coil, what is going to happen? The air will be cooled down until the temperature reaches as the saturated temperature. okay, saturated temperature, whereby the Phi or the relative humidity is 100%. So maybe what being sketched right here, this is the point where the air is saturated with moisture. Okay, the air is saturated with moisture. So that is the first phase of the process if we have condensate. So this could be, or this can be sketched from 1 to X in this case. So this is 1 at 30 degrees C, 80%. Then we are going to cool it down as accessible heat is involved up to the saturation point. Okay, up to the saturation point. Then if we bring down the temperature lower than this dew point temperature or the saturated temperature, so what happens? We are going to have condensate. Okay, condensate. And please remember, we are going to cool down up to 14 degrees C. So if we keep track with the process, 1 to X, this is point X, right? This at the saturation temperature. And then from X to point 2, which is 14 degrees C, then we are going to have condensation from the whole process from X to 2. Okay, so how much condensate that we are going to produce? The amount of condensate that we are going to produce is basically the omega X, which is equal to omega 1 minus by omega 2 and multiply by the M value. Okay, the actual value of mass flow rate. So that is what we are going to have. So this is the process of heat of cooling, where we have condensation. We might have cooling without condensation. If cooling without condensation, then we don't have any X value. It's only involving 1 to 0.2. From 0.1 to 0.2. And because of this condensation process from X to 2, then we are going to have the constant RH value of Phi value, whereby the Phi value of X is equal to the Phi value of 2. Okay, it's saturated. The air is saturated with moisture, which represent as 100%. Right? So as far as the mass balance is concerned, this is the mass balance of air. The air does not change any flow rate, mass flow rate, because we know that air cannot be condensed. Only water, moisture, or water vapor can condense. So this is the mass balance. The mass of air in is equal to the mass of air out and is constant. Whereby the water balance, we can see that what is the mass of air coming in, which is the m dot A1, omega 1, right? This is basically is m dot V1. And then we have the m dot V2 plus the amount of condensate. Okay? And if you want to get what is m dot condensate, which is m dot W in liquid, then we have this is equal to m dot A omega 1 minus omega 2. And then after that, we are going to look at the energy balance for this cooling with dehumidification. What is the energy in? The energy in, or the energy initial in this case, is m dot 1 H1. Okay, m dot 1 H1. And then what is the energy transfer by heat in? Is there any energy transfer by heat in? if you look right here, assuming that this duct is being insulated, meaning that the air will reject heat or the cooling coil, which is the refrigerant flowing inside the cooling coil. The cooling coil will pick up the heat of the air. So meaning that we are going to reject the heat of this air. So if we want to reject the heat of this air to the cooling coil, to the refrigerant, meaning that we are going to put the Q1 to, or the Q for the whole process to the right, because it's Q loss, okay, Q loss or Q out. That's why we are going to have this, our Q is to the right, and also we are going to have what is the energy out is m dot 2 multiplied by H2. So if we rearrange to get what is the Q out, this is equal to, yeah, one more portion is this. Okay, this energy from the mass of water condensate going out from the duct. So we have one more portion, which is the m dot w HW. Okay, remember, this is the condensate, liquid. If 14 degrees C, we are going to have compressed liquid. So the enthalpy of W right here, we should write as the HF at 14 degree C. Okay? So now we try to look at the example 14.6, discussing about this cooling and dehumidification. Air enters a window air conditioner at 180 M, 30 degrees C and 80% relative humidity at rate of 10 meter cube per minute. It's leave as saturated air at 14 degrees C. One of the moisture in the air that condenses during the process is also removed at 14 degrees C. Determine the rate of heat and moisture removal from the air. So basically, we want to see what is the Q absorbed by the refrigerant, okay, or the Q lost by the air. And then we are going to have the moisture removal, which is the m dot W. So this is the sketches of the system. This is what we have from the psychometric sketch. And if we look at the analysis, so from here, we could get what is H1 from the psychometric chart. We could get what is H2 also from the psychometric chart. And also we could get omega 1 and omega 2, and also the specific volume at state 1. This is the energy balance and the mass conservation. So from here, we are going to have the m dot A. The m dot A is equal to V dot 1 divided by V1. How to get the V1? So everything in here is from the psychometric chart. Okay? Everything that we are putting right here, everything we get from the psychometric chart. Okay, guys? So that is Q out. And then to get the actual, okay, the actual value is from the psychometric chart, and this is what I sketch. So this is 0.1. Okay, 30 degrees C, this is 30 degrees C. The relative humidity is 80, so that is 0.1. And then we are going, this 30 degrees C, okay. And then after that, we are going to have 0.2. 0.2 is 100% RH, P is 100, and the temperature is 14. So this is the 14 degrees C, the line of 14 degrees C. So that is 0.2. I think I did something wrong here. This is not 0.2 because this is not 14, this is 15. Let me see, 10, 11, 12, 13, 14. Yeah, I got it wrong, eh? Oh, wait. The 14 condensate removal, this should be the, oh, okay. This should be the dry bulk, the wet bulk temperature. Okay? This should be the, tengok semula, 50, no. 14 degrees C should be right here. Okay, guys, I think I got it wrong. Please correct it, eh? This point I plot is wrongly. This is represent not 50 but 16. It should be at 14 degrees C. It should be to the left. If I can let me see. This is example 14.6. Okay, let me see back. Example 14.6. Now we make the correction. Example 14.6. 14.6. Example 14.5. Okay, this one. Okay, so I need to move this point to the left. Guys, can you please do yourself? Just take note that this is wrong. Okay, what I have sketched is wrong. Okay, let me move. See it again. 14. So please correct it. I will try to correct it and then I'll give you one copy. So this is the one that we have. Okay, point 1 and then point 2 wrongly plotted. Then that is the process 1 to 2. 1 to X is the sensible heat. And then after that condensation occurs 1 to 2. And then we can get what is our value of Q. Okay? So that is the example for cooling and dehumidification. This is apa ni guys? Ini apa dia? Apa nama dia? Labu Labu this labu represent why we have certain people they said that if we put water inside this container, which is labu or labu sayung, right? It's made of clay. They said that when we put the water inside this container, we could have much more cooler water. So this the concept used to get this water to be cooled down. The process is being called as the evaporative cooling. Okay, evaporative cooling, whereby we know that the clay has a very fine porosity. Okay, we have the very fine porosity in this clay. So what happened? The porosity of the clay will be filled with water inside the porosity. Okay, they will fill with water. So as though that what we could have this type of container, which is labu sayung, as though that this labu sayung is acting as the wet bulk temperature. Okay, wet bulk temperature, whereby the porosity in the material will fill with water. And sometimes if you don't have a very smooth space, sometimes you can have droplets of water inside coming out from this the porosity of this labu sayung. Labu sayung. So this is called as the evaporative cooling. Right? So this is what we have. The evaporative cooling. So this is our jar made out of clay. So we could have the temperature is equivalent inside this. The temperature is equivalent to the wet bulk temperature, whereby we are having this wet bulk temperature from 1 to 2, the cooling process, right? As though that we are going to have this temperature equivalent to this wet bulb temperature. So this is the direction of the process. Okay, but in this case, we don't have any evaporative. We don't have any water evaporates because the point 2 right here is still below the saturation line. Okay, so very simple example for the evaporative cooling. Ni orang naik unta Kenapa orang naik unta pakai jubah walaupun panas because dia punya sweat itu, the sweat yang ada dalam baju dia, dalam jubah dia akan digunakan sebagai wet bulb. S2 is wet bulb. Desert dwellers often wrap their heads with a soaked water porous cloth. On the desert where the pressure is 1 atm, temperature is 15 degrees C, the relative humidity is 10%, what is the temperature of this cloth? So now the cloth is referring as the cloth dekat serban tu lah on top of the head. We call it serban. They used to soak with water. So what is actually happening? This is what we have at state 1, which is 1 atm, 50 degrees C. So this is 50 degrees C. Okay. And the water is being soaked. So this soaking represent as the relative humidity at 10%. Okay, so this is 10%. So this is the temperature of 50. Then what do we have? We are going to have the cooling process, whereby this cooling process is going towards the dew point. Okay, the dew point. So this is the process up to the dew point. And then what is being asked is to get what is the temperature of this cloth. Okay, so the temperature of this cloth is equivalent to the dew point temperature, which is T2 equal to the dew point. Sorry, it's a wet bulb temperature, not dew point. Dew point is here is the dew point. Okay, here is the dew point. Tapi this one is not dew point, this is a wet bulb temperature. Sorry guys. Dew point is to the horizontal, to the left is dew point. But this one is the wet bulb temperature. So we are going to have 23.8 degree. So at the environment of 50 degree, the head will subject or will feel the cooling at 23.8 degrees C. You guys, so that is for the evaporative cooling. Now we try to look at what we call as the adiabatic mixing of air stream. Now, this is actual condition happening in aircon system. Actual thing happening at aircon system. Usually the aircon system, for a centralized type of aircon system, we have the introduction of air, which is called as the fresh charge air, plus with the return air. Okay, fresh charge air plus the return air. So let's say this is our fresh charge air at point 1, and then this is point 2 or state 2 is the recycle or return air. Usually for human occupants, we need a fresh air. So in order to conserve energy, some portion of the air being cooled in the room, we are going to return it back to the system. So the amount of fresh charge is usually the amount that we need to supply oxygen for human breathing. Okay, for human breathing. So that's why we cannot totally take 100% of the air to be returned in the system. Only a portion. Okay, only a portion, because we need a fresh oxygen for human breathing. That's why we have the introduction of fresh charge of air. So assuming this one is a fresh charge of air, number 2 is the return air, which is a cooler, right? Cooler than this fresh charge air. The fresh charge air is taken from the outside air. Then it is mixed, right, in the mixing section, or sometimes we can refer that as the mixing chamber. Then what we have is the final state at state 3. Okay, final state at state 3. So this is the mixing process. So what we can look here is in terms of energy conservation and also in terms of the mass conservation. And this is called as adiabatic mixing. Why? Because the whole mixing section is being insulated. You can see right here, this shaded area or the shaded portion here is representing that we have insulated. Okay, we have insulation right there. So the mixing process can be presented in a psychometric chart, whereby the state 1, this is state 1. Okay, state 1. And this is state 2. Based on the omega 2, we get the we get the temperature of 2, then we get the state 2. Based on the omega 1, we get the state temperature 1, then we get the state 1. So what is coming out from this section, missing section, is state 3. So combined, this should be one arrow 1 to 3, and then another one is 2 to 3. Okay, the outlet is 3. So this is the energy balance. All right, the energy balance could be written as the amount of energy from state 1 plus the amount of energy at state 2, which is equal to the amount of energy at state 3. There's no Q involved because we assume it's adiabatic. So right here, what we could have is basically is m dot h1, this is m dot h2, m dot h1 plus m dot h2 equal to m dot h3. So this is the equation. The energy in equal to energy out. Right? So from this equation, okay, so we can write as this omega 2 minus omega 3 divided by omega 3 minus omega 1, which is also equal to the change in the enthalpy. Because this is basically is the gradient. The gradient of 1, 2 is equal to the gradient of 3, 2. Okay? Basically is the gradient. And this gradient, whether we are going to have the gradient in terms of delta H, or we could get the gradient in terms of delta W. Okay, so this represents the delta W, this represents the delta H. And we could have, this is the amount, the ratio of m dot A1 and the m dot A2. Basically, this analysis is to get how much should be our return air and how much should be our rest charge of air. And in this case, if one of these, if we don't have one at this portion of delta, and one we don't have the portion of this delta, because usually we will be left out with one of the omega is not known. Okay, and also we are going to have one value of enthalpy is not known. Okay, it's not known. If it's known, no problem. It's easy to solve it. But if we don't have one value of omega is unknown and one value of the enthalpy is unknown, then we have to do what is called as the trial and error in order to get this equation balanced. Okay, I will show you in this example. Okay, so we go to the last example right here, the mixing of conditioned air with outdoor air. Saturated air leaving the cooling section of air conditioning system at 14 degrees C at a rate of 50 meter cube per minute is mixed adiabatically with the outside air at 32 degrees C and 60% relative humidity at rate of 20 meter cube per minute. Assuming the mixing process occurs at pressure of 1 atm determine the specific humidity, the relative humidity, the dry bulb temperature, and the volume flow rate of the mixture. So we are going to have the analysis is basically to get the parameter at state 3, okay, of the mixture. That is state 3. So this is what we have of the mixing chamber. Then we could get what is state 1. So this is state 1 at 14 degrees C, okay, and saturated. This is the saturated point. 14 degree, saturated. Usually this is happening at the return air. Okay. Oh, sorry. This is return air. This is our fresh charge air. Okay. And then after that, we are going to plot the state 2 at 32 degrees C, 60%. So that is state 2. Right? So from here, we could get H1, omega 1, B1, H2, omega 2, P2 from the psychometric chart. And then from there, we could get what is M dot A1, M dot A2 based on the B dot A, B dot 1, and B dot 2 given in the question. So from here, we could write the M dot 3. Okay, M dot A3, which is the combination, the addition of these two mass based on the conservation of mass. Then we could equate this ratio in terms of the omega 2 minus omega 3 divided by omega 3 minus omega 1, put all the values of enthalpy omega, then this is what we have. So based on this ratio, okay, based on this ratio, so we need to do try and error for every enthalpy of 3 and also omega of 3. So by this using try and error, then we could yield the value of omega 3 and H3. So using the try and error method, then we could get what is omega 3 and what is what is the enthalpy of 3. Okay? So hoping this type of equation or this type of method is not going to be in the exam question, but usually in the exam question we will give you one of these value. Okay, we are not going to have two values unknown. Okay, because it's quite tedious and quite cumbersome and need a lot of time. So what we are going to do is we are going to give one of these basically on the state, either the state of 3, or maybe we could give you what is the value of omega 3, what is the state of 3 based on the moisture content. Right? So we just sketch. This is sketching again, 14 degrees, state 1, and then at our 32 degree at 60.2. And then we are going to combine that with the these 2 points, and we are going to plot what is our H3 and omega 3. So based on H3 and omega 3, right? The omega 3 is 12.2 gram over kilogram H2O. And then based on the plotting of our enthalpy value, then we are going to have this intersection. So this represents 0.3. Okay, so this represents 0.3. So the mixing process, we are going to combine from 1 to 3 and then 2 to 3. Okay, so that is the combination. From state 2, combine state 1, we are going to have state 3. That's end of our process. But in actual case, okay, we are not going to stop at only that point. Okay, in actual case, we are not going to stop at that point. For air conditioning system, basically we are going to combine the mixing chamber either with heating or cooling. Okay, we are going to combine this process either with heating or cooling. So maybe we have one more section right here. We could have Either we are going to have the cooling coil or we are going to have the heating coil. Right? So if we have that type of section, then we could have another process or another state in our psychometric chart. I will look for the question, what I mentioned just now. I will look at the past year's question that we could have a cooling process, which is more relevant to our country. And because we mix two flow, mix it, becoming M3, and then we are going to cool it and coming out at state 4. And at that state 4, we are going to put inside the room for air conditioning system. Okay? And then the last part of this case is to look at the wet cooling tower. So this is involving what is being called as the cooling tower to cool down the aircon system, but I'm not going to look it in detail. So as far as we are concerned right now, we are going to stop right here. But again, I will tell you there will be a next process after point 3, either cooling or heating. So let me sketch that on the canvas. Okay, and then let me take the picture of this. Not this one. Where is it? Okay, that's one. Copy this. Right? So what I can do right here is to combine this process. I will add up to make this question as an exam question. Right? I will add up another section right here. Okay, insulated. And I could either put a heater. So this is heater. Okay. And this is our section. And this, let's say this is section 4. And this is what we are going to have in terms of omega 4 and H4. Okay. So this is for heating process. Okay, for heating process. So if heating process, then if there is only sensible heat involved, then we could get another line right here. Horizontal line for heating process. Horizontal line for heating process, which represent 0.4. Okay? So that is for the heating process. And another case, we could get also cooling process. So if cooling process, what we could have, we have another section right here represent the cooling process, blue color. Assuming still adiabatic, there's no heat loss in this section. So we are going to have this state 4. And we are going to have the cooling coil. This is for the cooling process. Okay, cooling process. Right? So right here, we could have our omega 3 and H3. The flow going coming up right here. And if we incorporate this process at our psychometric chart, if only involving let's say it's involving, let's say this is saturated. Okay, let's say this saturated, meaning that we are going to have a line horizontally to the left. If saturated, we are going to touch the 100%. If saturated condition. If we have condensation, okay, if we have condensation, so we need to add up one more line at the saturation line. It all depends on what data is given. For the heating process, of course, that's it, what we have. Maybe if I put spray, this will make it complicated, it's quite long. Yeah, I could put here as spray for the humidifying process. This is for the dehumidifying process. Okay, so I could add up one more right here, and then maybe what we could guess from this point going up. So I can put a lot of combination of processes in the air conditioning system. But the very basic one, this is related to our country in Malaysia. Country such as Malaysia. This is what usually happen in air conditioning system for a central cooling or central air conditioning. Okay? So I think that's it for the psychometric. So what I'm going to do right now is to look at one question from past years, 17, 18, 02, to be solved together. So guys, please make your psychometric chart available. Any question before we start? Guys, any question before we start? Ada soalan tak? Tak ada? Okay. So this is the question from past year's SMQ for psychometric. A sling, I better, that is the part A. Where is the part A? Okay, part A. Okay, this one. Cold water flows through a metal pipe which is not insulated. The pipe is located in an ambient air which is at higher temperature and humidity. What do you think would be observed on the surface of the pipe? Describe briefly the reason for this. Okay, we have a pipe, flow of cold water, not insulated. The pipe is located in an ambient air where the higher temperature and humidity. Kita ada kita punya cool air, cold water flowing, and then dekat luar tu kita ada apa? Kita ada kita punya ambient condition whereby the temperature is higher. Okay, higher temperature and humidity. What do you think would observe on the surface of the pipe? Can anyone describe that? What is going to happen? Anybody can answer that? Guys, what do you think will happen? In the same, this is the same case as we buy a drink, a cold drink, right? And then we try to drink it, because you know that is the condition. Inside the glass or inside the container, cool water. Outside is the environment, we have hotter than the cold water. The temperature is higher, the humidity is high, the temperature also high. So what happened, do you think? Guys? What will happen to the pipe? The surface, the outside surface of the pipe. Guys? Tak ada orang ni. Ada orang, tak ada orang. Water droplets will form. Okay. Which is also known as the sweating, You are also known as the sweating phenomena. So can you explain how this sweating will occur? This could be explained in the TS diagram. If I can sketch on the TS diagram. And let's say, this is our TS diagram. Sorry. TS, as we know that usually water vapor is at superheated. Okay, superheated condition. This is our point 1. This should be our, what pressure is this? This is PV. And this is our T. And this is our PG. Okay? And this is our dew point temperature, TDP. So if we have this environment having this type of collision of state 1, so when it get into contact of the surface of the pipe, if the surface of the pipe, the TP, is less than the T set, okay, at PV, what happened? We are going to have a cooling process right here. And if we cool down until the TP is equal to T set, equal, right? There's no condensation. But when the TP is less than the T set, then we have this type of condition. So we are going to have sweating, condensate occurring outside the surface of the this pipe. Okay. So next question, part B. A sling psychometer shows a dry bulb and wet bulb temperature reading of 25 degrees C and 20 degrees C, respectively. The atmospheric pressure is 101.325 kilopascal using the psychometric chart and by calculation. This is not by. This question should be, you can use chart, or you can use the combination between chart and calculation. Because some of this parameter given right here, you need to do some mathematical analysis. Not everything could get from the chart. Okay, that is the meaning of this question. Bukan kena buat everything, buat dalam chart dan everything kena tunjukkan dalam calculation. Some of them you are going to get from the chart, and some of them you are going to get from the equation. Right? So now we have a state. What is our state? 25 degrees C and 20 degrees C. So let us look to this psychometric chart. We are going to plot 20 and 25. 20 is the red bar. So where is 25? So let us look where is 25. So this is 30, 20. So this is 25. You see, guys, I got a ruler very straight, but it seems that this diagram is being skewed. So dia tak really vertical. So let me see. But this is the diagram that we are going to use during the exam now. Let me see if I have another version of this which is could get very vertical. Ini yang saya bagi semalam kan, guys. I need to tell Encik Mr. Kamal that the diagram that is given to us is not well scaled. You see, this ruler is 90 degree, but when I put it adjacent to the 25 degree C, I'm not going to have a straight line at 25 degree C. A bit angle, so this diagram is not good. So I will let Encik Kamal knows about that, and maybe we are not going to use this diagram during the exam. So let me put another diagram that I have. Let's see here, mana dia? Psychometric online psychometric chart, original. Let me see this one. This is the original one. Okay, let me zoom in, out. Okay, let me select all, copy. This one. This one. Delete. Where is the question? Okay. Paste. All right. So let us check whether this is okay or not. Okay, let me put the ruler. Sama juga Still the same thing. So I need to adjust a bit. Okay. All right. It's not 90 degree, tapi about 88 degree. So based on this, I need to put it at 25 degrees C. So this is our 25 degrees C. Let me sketch that line. So that is at 25 degrees C. Guys, please do it together with me. This is 25. This is 25 degrees C. And then we have 20 degrees C. 20 degrees C, as for the wet bulb. So let us look where is the line of wet bulb. Okay, this the dotted line is the line for wet bulb. So let me get that. Okay, this seems to be good. And I'm going to put it at 20 degrees C. Sorry. Okay, so this is 20 degrees C. A bit lower. Okay, so let me sketch that. Okay, this is 20 degrees C. This is 20 degrees C. So this is our point, the intersection. Okay, the intersection, that is the point. Then the first question is to get what is the omega value. So let us put the ruler horizontally, which is 0. Can we get that? No. So we need to get it parallel with the omega value. Okay, this one should be okay. Omega. Okay, so this is the intersection. That is your omega value. Then let me sketch that to the right. And maybe I could have let me undo that. Undo a very thin line there for easy reading. Okay. So there is the omega value. The omega value should be about 12. This is 12. This is 14. We should get about 12. 12 is 12.5. Okay, this is 12, 12.5. This is 14, this is 13. It's about 12.5. Okay, the omega is equal to the omega is equal to 12.5, a bit, yeah, about 12.5. This is gram over kilogram of dry air. Okay, so that should be our value of omega. The next question is to get the RH. So the RH from here, the RH, this is 60. Okay, this is 60. This is 70. And I could get like about 63. Yeah, about 63. So the omega value, which is equal to RH, I get about 63 degree, sorry, 63%. Okay? And then how to get, the third question is to get the PV. This PV we could not get from this, there's no pressure here. But what we can do is to get the value by putting the, so this is number one, this is number one, this is number two. And number three is to get the PV, okay, the pressure, the partial pressure of water vapor at that point, right? So in order to get the PV, then we have the phi value. The phi value is equal to PV over PG. Okay, and what is PG? The PG is equal to P at P set at 25 degrees C. P set at 25 degrees C, and from the steam table we could get this as 3.1698 kPa. Okay, and once we have the PG, then we get the PV. So we could solve here. The PV we are going to have is about 1.997, 1.997 kPa. So that is number 3. And then for number 4, we are going to get the dew point temperature. Number 4. T dew point. Okay. So where is our dew point temperature? The dew point temperature is the line whereby from this point we are going to draw a sketch a line to the left. Okay, to the left. So let me put the ruler again. So that should be our point there to the left. So this should be our TDP. Okay, so we are going to have, this is 15, 16, 17, this is 18. So it's it's before 18. Okay, maybe I can put right here the TDP is as 17.5. Okay, 17.5. The TDP is equal to 17.5 degree C. So this is for number 4. Right? And then we are going to have the enthalpy of that point. So let me adjust. So where is our enthalpy line? So this is our enthalpy line. Let me put it a bit Susah tak boleh dapat sama. Okay, it's about this Okay, kalau saya boleh adjust lagi. No. Bawah lagi. No. So this is the best line. Okay, this is the best line. So let me put at that point. Right? So what I could get from here to get the enthalpy value, so I need to get from there and make sure that the line is equivalent on top and also at the bottom part for the enthalpy. So that is the enthalpy right here. So this is the enthalpy, this is the enthalpy. Okay? So enthalpy right there is about, this is 50, 51, 52, 4, 6, 8. So it's about 57, a bit more than 57. Right? So let I put there as a 57.2. Let's say 57.2 kilojoule over kilogram. So this should be number 5, the enthalpy. Right? And then the next question is to get the percentage of number 6, the percentage of saturation of the air. So number 6, this is number 6. This is given as the psi, which is equal to omega divided by omega G saturated. Right? So as for the omega G, what is omega G? Assuming it's saturated, the omega G is equivalent to the formula is 0.6622 multiplied by the P of vapor divided by the atmospheric pressure minus P of the vapor. And in this case, we are going to assume that the vapor is saturated. So this should be our PG, and this should be our PG. Okay, the PG we have defined just now. We got around 3.1698, and this will give us the value of omega G as the 0.02009. 0.02009. This is in terms of kilogram. This is in terms of kilogram for every kilogram of dry air. So from here, we could get the percentage of saturation. We get 61.22%. Okay? So that is for part A. So this is what we have. The part A is basically given a state. Okay, given a state. So that is the state. Get all the properties. Some properties we could get straightforward from the psychometric chart, but there's 2 parameters that we need to get from the calculation, which is the percentage of saturation and also the partial pressure of water vapor. So that should be by calculation. Okay? So next, what we are going to have is we are going to get for the part C. So let me delete that. Okay, for the part C, this is part B. Let me get the part C. This is part C. This one. Yeah, this is involving a cooling process. Okay, involving a cooling process. Right? So let me copy that. Paste it. Part C. Copy. Paste it. All right. So this question, part C, is continuation of part A. So we have the part A, is now we have sketched it. The atmospheric air in part B is cooled at constant pressure until it becomes saturated at a temperature of 10 degrees C. Okay, lihat the atmospheric condition, atmospheric air in B, we are going to cool it down until at constant pressure, uh, it becomes saturated at temperature of 10. So if we look here, so now we could write here, this is our state 1. Put here, this is state 1. Okay, state 1. And then we are going to cool it until we have 10 degrees C. So if we cool it down until 10 degrees C, where is 10 degrees C? So this is 10 degrees C. Sorry, 10 degrees C should be okay, 90 degrees, 10 degrees C. So this is our 10 degrees C. Let me adjust it a bit. Okay, so I'm going to have this line. It represents 10 degrees C. Cooling process. Sorry. Okay. Sorry, guys. Aduh. What happened? Come on. I'm trying to sketch. Aduh. Tak jadi lah, guys. Notice. Dia lari-lari pula. Aja je dia. There, you see? What happened? Okay, let me try to do it again. 10 degrees C. Let me start from here, boleh tak? Oh, tak boleh juga. Okay, what happened? Aduh. Something is not right. Sekejap, guys. Misalnya. Again, please. Bismillah. Okay, see? I thought I've locked it. Yeah, I've locked it. Whiteboard saya pun dah pening ya. Okey lah, so macam mana saya nak buat? How I'm going to sketch, tak apa. So I'm going to sketch very roughly with my free hand. Okay, with my free hand, 10 degrees C. So I just put the point. This is 10 saturated. This is point. Oh, I know what happened. I really know what happened. Saya guna mouse. Mana boleh guna mouse? Kena guna stylus. Aduh, sorry lah guys. Sorry guys. I kena mouse. Betul. That's right. This is 10 degrees C. Right? So what happened actually, kita ada satu proses from 1 to, let's say this is point, nak nama apa X. Okay lah, try to put this. Nak put X ke nak put 2 I put is 2 lah. 2. This is point 2. And then another process, dia ikut the saturation line, which is the humidity is 100%. Okay, so this is point 3. This is point 3. So that is our process. We have the cooling process, 1 to 2 involving sensible heat, and then 2 to 3 involving latent heat. Ada condensation. 2 to 3 ada condensation, so it's latent heat. Alright? So that is the process. So the first question that we need to know is to get what is the omega 3. What is the omega 2 ataupun the omega at the this one omega, in this case the omega 1 is equal to omega 2 omega 1 in this case we are going to have the omega 1 is equal to omega 2. Right? And then how to get the omega 3? The omega 3 that is being asked for the first question. Oh, ada lagi proses. Saya terlupa Sorry guys. I got one more process After getting to the 10, the air is then heated at constant pressure until the bulk temperature is raised to 18. So I need to put another one process which is at 18 degrees C. So I need to put back my ruler and get it at 18. So this is 20, 19, and this is 18. Today ada 18. So this is at 18 degrees C. 18 degrees C. Okay. So now let me sketch from that point 3 to the new point where we heat it up at 18 degrees C. So horizontal. Let me put it as close as horizontal. This one. Okay. So that is the point. Okay, that's one. Then I have another line 3 to 4. Okay, so this is 4. Betul. So that's we finish with this, the process. So 1 to 2, sensible heat cooling, 2 to 3, latent heat, and then 3 to 4, heating, sensible heat. So we have 3 points. Ada 4 points. So now the question seterusnya is to get the W3, which is equal to the omega 3, which is equal to the omega 4. This is number 1 of part C. C part 1. So straightforward. We try to get the value from here. Kita buat, try to project the point 4 and point 3. The 0.4 to 0.3 sampai kepada omega. So this should be our omega value. This is our omega value. We will get the omega value is about 7.75. 7.75 gram over kilogram of dry air. Be careful guys, dia punya unit dekat sini, you need to be careful. The unit sini ada plus, ada yang the unit here is mesti nampak maybe bigger. This is in kilogram. Unit for omega here is gram. Okay, gram. The unit for omega there is gram moisture over kilogram dry air. So be careful. So that is the value. And then for number 3 is to get the wet bulb temperature. So what is the wet bulb temperature? The wet bulb temperature maknanya sekarang ni the final. So kita kena dapatkan sini lah. So kita kena make a line which represent that. Okay, so try to do it. I'm just giving you the final value that I have. So number 2, I'm going to have the wet bulb of state 4, which is equal to 13.5. And then number 4, the percentage of saturation. Again, you need to get your formula of Wg just now. I've shown you in part B. Then you will get the percentage of saturation right here is equal to 38.58. Okay, and then number 5, we are going to get what is the delta omega from the state 1 and state 3, the only 2 omega involved. Omega 3 is equal to omega 4. Omega 3 equal to omega 4. Omega 1 is equal to omega 2. So the difference in relative humidity, you will get 14.55, 4.55. 4.55 gram for every kilogram of dry air. Okay, and number 6 is to get the delta H. Okay, number 6 is to get the delta H. What is the change of enthalpy for the whole process? Then we get the delta H for cooling, which is equal to H1 minus H3. Okay, we already have the H1 from part B. Now we get the new H3, which is about, H3 is about 30 kilojoule over kilogram from the chart. And then from here, we will get the delta H cool is 27.2 kilojoule over kilogram. And then the next delta H that we want is the delta H for heating. That is cool. Then delta H for heating, which involving 3 to 4. So this should be H4 minus H3, and the H4 from the chart, we are going to have 38 kilojoule over kilogram. And in this case, we have already get the delta, the H3. Then in this case, we are going to solve for the heating as 38 kilojoule over kilogram for every air. You guys? So that's it for the exam question for psychometric chart. Please have a try and try to get the same answer what I have shown you just now. Okay? Any question? Please remember, if you look at the exam question, please submit the psychometric chart together with your examination answer script for evaluation. So what you need to send also during your solving of this question, you need to send in the psychometric chart, which having all the plotting that I have shown you just now. Okay, with all the plotting. So this will be given marks in terms of plotting. Right? Ada soalan guys? Guys, ada soalan?
No, sir.
Okay. So if no question, let me give you the attendance link.